Good evening, everyone. My name is Apurva Sharma. Today, I'll be talking about the topic deep learning framework with time series analysis methods for runoff prediction. We'll be starting off with the introduction and the past work that has been done in this domain. Then we'll take an overview of whatever the research work was being presented in that particular paper. Then we'll go through the necessary terminologies that we need to understand the work that has been done. And finally, we'll move over to the evaluation metrics and the results. Coming down to introduction. So first of all, what is runoff? What actually runoff is? So runoff forecasting is a sort of time series prediction problem with a series of past runoff data is taken as the input and a fixed length series of future runoff as output. Now runoff data consists of two types of data: the water level data and the discharge series data. Now, why runoff forecasting is important, and why are we doing it? So runoff prediction is an important research field for hydrology, particularly at the places, particularly at the flood prone areas where we actually need to predict the level of water in the future time, so as to adequately plan water resource so as to adequately plan other things. And it is also important for water resource management and to prevent geological disasters. Coming to the past work that has been done, a major amount of work that has been done in this domain has been involving machine learning systems. But one of the major drawbacks of the machine learning systems is that they require a significant amount of manual effort, including sophisticated model construction, featuring the engineering output. A lot of feature engineering has to be done, which requires a lot of domain knowledge. Since domain knowledge is something that's not easily available in the market, so machine learning system got its own limitation in this particular domain. Now, also the current prediction models that are being built in the past generally don't take into account the seasonal trends, the residual part of the time series data. So we'll be covering all these aspects and integrating it with the deep learning model in this particular paper. Coming on to the challenges, there were two major challenges for implementing this approach. First, the runoff, the type of data that we need. The runoff time series data generally suffers from high amount of missing data and high intermittency. That means there is a large amount of outliers or a large amount of null values for the days we couldn't record the data due to some failure, due to some repair work going on. So, the first challenge is this. Coming down to the second challenge, we wanted to build a deep learning based solution that is robust enough to be applied to multiple reservoirs, not to a particular reservoir. So we wanted to generalize the model and make it robust so that it can be applied to various hydrological plants as well. Coming overview of the work, majorly four things are done in this particular paper. The first one is a simple and a powerful deep learning. The first is the simple and powerful deep learning model based on time series analysis methods was proposed for daily runoff prediction. The quantity of data that we actually required for deep learning training was analyzed and detected by mutual information. What mutual information is, I'll be covering it in the next slides. The seasonal trend decomposition methods can further improve the accuracy of runoff prediction, where the time series data is decomposed into three, either by using additive decomposition or multiplicative decomposition. And finally, time series analysis method combined with deep learning frameworks such as RNNs or LSTMs can unleash the greatest of the potential of artificial intelligence in the field of hydrology. Coming down to the necessary terminology, what is mutual information? So mutual information is a metric that is used to express the amount of dependency or cooperation among different variables. It is built on Shannon entropy of information theory. As you all are aware what entropy is, is given by the equation present in this slide. H of x is equal to minus of n summation I1 to n pi into log of p, where p is the probability of that particular event. The mutual information between, now consider there is an event x and there is an event y. So both the events will have some amount of information that is being shared between them. So the mutual information that is present between the variable x and variable y can be determined by this particular formula I of xy. So we'll use mutual information to decide we'll use mutual information to decide the length of input data that we require for predicting the future runoffs. Coming down to seasonal and trend decomposition, as we all know, the time series data are generally decomposed into three things: the seasonal part, the trend part, and the residual part. Generally, there are two types of decomposition: additive decomposition, multiplicative decomposition. We can write additive decomposition as yt equal to s of t plus t of t plus rt, where yt is the time series data, st is the seasonal part, t is the trend part, and r is the residual part. And for the multiplicative decomposition, these all three terms will get multiplied. Multiplicative decomposition, sometimes we often use multiplicative decomposition by taking log, which later get converted into additive decomposition. So like additive decomposition of log of seasonal, trend, and residual part. Here we'll be using the additive decomposition straightly. Now coming down to what long short-term memories are. Before going to long short-term memory, I'll briefly describe what recurrent neural networks are. So recurrent neural networks are a type of neural networks that were mainly built to identify the relations in sequences like text, speech, audio, the sequential data where the future prediction is dependent on the past prediction as past input data as well. Now, recurrent neural network generally tends to suffer from a problem of vanishing gradients because as a result, using RNN, we couldn't capture the data for a larger duration of time. Long short-term memories were then introduced to solve this problem. LSTM is capable of remembering long-term dependencies that are required for complex tasks such as speech translation. Information passes through a mechanism known as cell state. Each cell state is responsible for one particular type of task. LSTM generally uses three types of gates, namely the input gate, the output gates, and the forget gates. Here in the picture, the rectangular block shown is the basic structure of LSTM block. Many such blocks are then later combined to extract the information, remember the useful information, give weightage to the most important information, and finally gives the prediction. Coming to the proposed method, the proposed method majorly consists of two major phases. The first phase is the application of time series analysis method, where we use mutual information to determine the length of to determine the fixed length of input data and to identify what are the major important feature for us to perform feature selection. The second phase is the prediction phase, where where three LSTM architectures are being combined together to generate a single prediction. We can see through this flow chart. This is our overall pipeline. So initially we'll get the original daily runoff series data. We'll use mutual information method to compute the number of fixed length data and the important features that are important for us. Now once we get this feature, we'll do the STL decomposition of that time series data. We'll decompose it into seasonal series, the trend series, and the residual series. Now for each of these three components, we'll train a separate LSTM architecture. So one architecture will be for seasonal series, the second one will be for the trend series, and the third will be for the residual series. And since we were using the additive type of decomposition, for reverse decomposition, we'll just sum all the three outputs and generate the predicted runoff series in the last step. So this is the entire pipeline of our proposed methodology. Coming now to the data set description, we took data set for two hydrological stations, Yaicheng and Hankou stations that are located in the course of Yangtze River. For both the hydrological station, we gathered some basic information such as the control basin area, the multi-annual average water level, what is the ratio of maximum and the minimum flow, and what is the amount of maximum one-day flow that is being happening over a long period of time. Coming now to the sort of data pre-processing, obviously every machine learning, deep learning method requires some sort of data pre-processing. Here first, as we mentioned it earlier, that there is a large amount of missing data outliers. So for all those missing data and outliers, we use linear interpolation to fill out those values. Coming now to second, min-max normalization. We scaled all the values between 0 to 1 using min-max normalization. Min-max normalization is calculated using the formula xn equal to x minus x minimum divided by x maximum minus x minimum, which is where x maximum and x minimum denote the maximum and the minimum value of the input data. Coming now to the evaluation metrics, there are mainly four evaluation metrics that we'll be considering. The first is the RMSE, the root mean square error, that is calculated by the this given formula. The second one is NSE, that is the another evaluation matrix, that is 1 minus summation of yi minus yi cap. Yi cap is the predicted value and yi is the actual observed value. Second is the mean absolute error, that's just the deviation of the predicted value from the actual value, and second is the MAPA, that is again the deviation of the actual value from the predicted value in terms of percentage. Coming down to results and analysis part, this particular graph shows the seasonal decomposition of Yaichang water rivers. If we look at the seasonal series, we can see that like the seasonal, there is always a there's a continuous peak after a certain duration of time. The seasonal part of this particular series is really well extracted. Coming down to the residual series, as we always expect the residual to have a mean 0, and it is already clearly visible that the mean of this particular part is also 0, so we can consider that the series to be almost stationary. And looking at the trend series, the trends are generally not that significant for this particular case. Similarly, the seasonal decomposition of Hankoy water level series, we'll looking at the seasonal series, it's again extracted properly. Residual series is much more deviated as compared to the one from the Yaicheng water level series. And trend, again there is no such no significant trend is observed. Prediction of now coming to the final prediction of Yaicheng water level series. The orange line shows the predicted water level, and the blue line is the actual water level. So we can see that the blue line is very properly overlapping the orange line. That means the our prediction are very much accurate and very much near to the actual water level that were being observed. For training, we took the data from about 1999 to 2020, that is around 20 years of data was used. And to make sure that the model didn't overfit, we used 25 25, we set k equal to 25 for cross validation. Similarly, for the Hankoy water level series, in the initial part, we can see that the blue and the orange lines are properly over lapping, but our model wasn't able to predict properly when the water level increases above a certain value of 27.5. There is, as you can see, that there's a significant difference between our prediction and the actual Z value. Coming now to the and similarly for the Yaicheng discharge series, we can see that the blue and the orange lines are properly overlapping. The error percentage was varying between 1 to 7.5% for both the cases, and that are pretty much low as compared to the methodologies that were we using earlier. We can see these are the results that we got. If we'll consider for the hydrological station Yaichang, if we'll take the only the Naves LSTM, the Nash circle efficiency coefficient NSE comes out to be 0.8754, whereas our proposed model comes out to be 0.9694, which is a significant improvement. Similarly, the RMSE score got decreased, the mean absolute error got decreased by significant amount. The mean absolute percentage error came down from 6.0 to 2.09, which is a significant improvement. And similarly, it's for the water level for the Yaichang, and similarly for the discharge and the water level for Hankook. So we can see that for every aspect, the proposed model is performing far better than the Naves LSTM or with the LSTMs with mutual information. So there's this particular approach has shown a significant improvement over the earlier methodology. Coming down to the conclusion part, LSTM networks have been popularly applied to the hydrology research because of their powerful predictive capacity, as they're able to remember even a long-term dependencies that are often required in these types of domain work. In this paper, we have combined the deep learning framework and LSTM network and two time series analysis method under two different hydrological stations. One of the major challenges for this is to the amount of data. Generally, the LSTMs requires an extensive amount of data, so the limited quantity of data was another challenge for this. And this particular proposed framework is also able to handle non-linear complexities which earlier methods were not able to handle. This developed framework can easily be generalized for multiple hydrological stations, as it is purely based on historical data only. So yeah, thank you.